안녕하세요. IMU 승급기념 국제학회 키아스 기조강연의 좌장을 맡게 되어서 영광입니다. 우선 오용근 교수님의 오용근 기조강연의 키아스 기조강연에 발표를 해주실 분은요. IBS 단장님이시고 포항공대 교수님이신 오용근 교수님이시고요. 오용근 교수님은 상대적으로 이제 신생 학문인 사교기학, 사교위상수학 분야를 수립하신데 큰 역할을 담당하셨습니다. 그래서 특별히 라그랑지안 인터섹션 플로우 티어리의 파운데이션을 만드셨고요. 해밀토니안 다이나믹스를 공부할 때 중요한 인베리언트인 스펙트럴 인베리언트를 이제 창조하셨고요. 그리고 토폴로지컬 해밀토니안 다이나믹의 공부를 시작을 하셨습니다. 그래서 오용근 교수님의 양력을 간단히 이야기하도록 하겠습니다. 우선 1983년에 서울대학교 학부회를 졸업하셨고 1988년에 UC 버클리에서 박사를 졸업하셨습니다. 그리고 2014년까지 유니버시티 오브 위스콘신 메디슨에서 교수로 재직하시고 귀국하셔서 현재 IBS CGP의 연구단장님 그리고 포스텍 수학과의 교수님으로 재직하고 계십니다. 수상 경력을 간단히 이제 말씀드리면 2000년에는 이제 젊은 수학자상을 수상하셨고요. 그다음에 2006년에 ICM에서 초청 발견을 하셨습니다. 그리고 2012년에는 경암상, 그리고 2019년에는 한국과학상, 그다음에 2020년 올해는 이제 호암상을 수상하셨습니다. 그래서 키아스 기조강연에서 이제 발표하실 제목은요. 컨택트 다이나믹스, 서머다이너믹스 앤 컨택트 토폴로지에 대해서 이제 발표를 해주시겠습니다. 네.
예, 이렇게 초청해 주셔서 감사합니다. 이렇게 우리 한국 수학이 장적의 발전을 한 그 기념으로 이런 우리 학회를 여는데 여기에 초청받게 강연되게 돼서 영광으로 생각합니다. Okay, so this is the title of my talk today. And this is the overview of what I'm going to talk about today. I'll first talk about some background, historical background of what I'm going to talk about today. So, information theory and statistical mechanics, and then contact geometry and thermodynamics, and simplex contact reduction and reduced entropy generates thermodynamic equilibrium, and then I'll talk about Van der Waals model and phase transition. Okay, here is some important historical development related to what I'm going to talk about. In 1948, Shannon's classical paper, A Mathematical Theory of Communications, in the Bell System Technical Journal in July and October 1948, established the discipline of information theory as a quantitative mathematical theory. And then after 10 years, in 1957, the statistical physicist E.T. Jaynes interpreted statistical mechanics as a form of statistical inference by implementing Shannon's information theory. And then, after around maybe 20 years after, the dynamical system, the mathematician working on dynamical system, Hermann suggested the contact geometry to be the mathematical framework for the thermodynamics in his 1973 article. So the main purpose of the present talk is to explain how we can combine these three historical developments into a canonical derivation of thermodynamics from statistical mechanics. Actually, thermodynamics is somewhat mysterious, actually, physical theories. Its foundation, I think it's, even in physics point of view, it's still quite mysterious. So I attempt to explain how one can derive thermodynamics from the first principle of statistical mechanics, That's the goal of this talk. So let me start with the seminal paper, Information Theory and Statistical Mechanics, in which he implemented information theory into the framework of statistical mechanics. So the first paragraph of his paper goes like this. Information theory provides a constructive criterion for setting up probability distributions on the basis of partial knowledge and leads to a type of statistical inference. So he wanted to regard the statistical mechanics as some kind of system of statistics, which is called the maximum entropy estimate. It is the least biased estimate possible on the given information, i.e., it is maximally non-committal with regard to missing information. If one considers statistical mechanics as a form of statistical inference rather than as a physical theory, it is found that the usual computational rules, starting with the determination of partition function, are an immediate consequence of the maximum entropy principle. And whether or not the results agree with the experiment, they still represent the best estimates that could have been made on the basis of the information available. And then he actually explained how the information theory can be implemented into the foundation of statistical mechanics. Okay, so let me now talk about what the information theory Shannon invented. So we want to construct the function I, which measures the uncertainty of the information saying X is in some A contained in some measure space. Beta is some measurable subset, A in B. So here is the definition of information measure. The information measure, I mean, it's like a measure, but that satisfies the following four properties. So it is a function of this probability of, the mu is a probability density. And then it's a non-negative quantity. And the smaller probability is, the larger the information is. Here the information should be regarded as the value of information. And if A and B, the events A and B are independent, then the information amount of both events can happen simultaneously is additive. And then we know that the increasing continuous function f satisfying this kind of a rule is nothing but a negative logarithm. And that's the way how the logarithm appears so often in the information theories. So now we consider the general measure space, such as the particle phase space, the cotangent bundle with the Liouville measure. So you look at the classical Hamiltonian phase space, and this phase space carries a natural so-called Liouville measure. So this classical phase space is naturally a measured space. And then we need to consider the so-called relative information measure rather than Shannon's original absolute measure using this background measures. So here is the definition of relative information measure. Let gamma nu zero be a measure space, and rho is a probability density. And we define the relative information measure denoted by I as a function of rho, the probability density, to be, that D should be rho, sorry. So that's the logarithm of Radon-Nikodym derivative. We have a background measure, so you can take Radon-Nikodym derivative for any probability rho. And then this information entropy is nothing but the integral of the multiple of information measure times the probability density. So in other words, it's nothing but the average of information relative to the given probability density. And in more formal mathematical terms, this is also written, known as Kullback-Leibler divergence of this probability law relative to the given background measure nu zero. But I'm not going to use this term in this talk. I'll just use relative information measure. Okay, and then how I'm going to use this kind of information theory into the derivation of thermodynamics, I need to explain a little bit about contact geometry. And this is the picture of the contact structure. The contact manifold is some odd-dimensional manifold. For example, the odd-dimensional Euclidean space. You regard the classical phase space added by another variable, z. And that has a very natural one form called the contact form, that is dz minus pi dqi. And then the kernel of this one form defines some codimension one distribution, hyperdistribution field. And the figure is the picture how this hyperplane field distribution changes as these coordinates z, p, and q move. So there is some kind of, at this point, you are given hyperplane, and this hyperplane moves as the point changes. And this hyperplane field satisfies some non-degenerate condition, and then it's called the contact structure. Now let's talk about, first talk about equilibrium thermodynamics. The local description of thermodynamic phase space is given by the thermodynamic variable in physics literature. There is no intrinsic or abstract definition of thermodynamic phase space. The physicists already use these variables and then explain the thermodynamics in terms of these variables. So the first law of equilibrium thermodynamics can be described as du equal TdS minus PdV. This is so-called energy representation. So the way how we can interpret the first law of thermodynamics goes as follows. You're given some thermodynamic phase space defined by 5 independent variables, U, T, this is the simplest one, sorry, U, T, S, P, V. Here U is the internal energy, and T is the temperature, S is so-called thermodynamic entropy, and P is the pressure, and V is the thermodynamic volume. Now, this first law looks very similar to the vanishing of contact form. And I think that the Hermann's motivated largely by this similarity and suggests the contact geometry could be useful to describe thermodynamics. So here is the contact geometric interpretation. So you look at the contact manifold, R5, with the contact form that is du minus TdS plus PdV. And then I'm going to talk about this, the second correspondence, which can be interpreted as second law of thermodynamics, which reads that Legendre submanifold, which I'm going to give you a definition later, can be interpreted as thermodynamic equilibrium states. The Hermann's proposal is exactly, as a simplex geometry is a useful mathematical framework for Hamiltonian mechanics, contact geometry should be the mathematical framework for thermodynamics. After Hermann's proposal, there are tons of articles appeared in mathematical physics journals, and many of them try to realize these Hermann's proposals, but it ended up with just translating the given thermodynamic law into this new mathematical language. So thermodynamic phase space so far exists only abstractly described through coordinates in the literature. One of the main goals of the present talk is to explain TPS as a contact manifold by a canonical and covariant reduction process, starting from the kinetic theory phase space, which is the cotangent bundle of the space of probabilities. So the approach I'm taking is kind of field theory, a very familiar field theory approaches in field theory in physics. So I want to take the probability space as the space of field, and then I want to do some classical mechanics on this field space. And the many-body particle phase space I will call statistical phase space. That's where the statistical mechanics occurs. Okay. And actually, this kind of attempt was not new. Here is one good example of this kind of attempts. This is some quote from Grammer's paper. Okay. So here is the question Grammer posed in his paper, and I'm just quoting here. Again, the main difficulty on this route is in the reduction process. The question that arises on both routes is the following. How shall we make the reductions in order that the essential features of mechanics put into the original microscopic formulation is kept intact, and the comparability with the thermodynamics of both microscopic and mesoscopic formulations is guaranteed. So one of the main goals of the present talk is to explain this reduction process as a reduction in the simplector contact Hamiltonian geometries. So I'm going to make two reductions. One, the so-called simplector reduction to derive the background thermodynamic phase space. So this step can be regarded as derivation of non-equilibrium thermodynamics. And then I'm going to use this information entropy to define the equilibrium states. So this is the kind of a contact reduction and corresponding to the second law of thermodynamics. Okay, so let me briefly recall the definition of simplectic manifold and some contact manifold for those who are not familiar with this. And N is general smooth manifold. Oh, by the way, so what I'm going to discuss can be applied to any smooth manifold, not just on this classical particle phase space. So this formalism can be applied to many other thermodynamics that appears in physics literature, like black hole thermodynamics. And so what I'm explaining can be applied to that kind of setting. And then this cotangent bundle carries a natural geometric structure so-called Liouville one form, which is this one form, pi dqi, in canonical coordinate. And the canonical symplectic form is just the differential of this one form. And that is just some two form. You can see that this form is non-degenerate. That's okay. And then the one-jet bundle is the other dimensional enhancement of this cotangent bundle. It's abstractly defined as the following. So J1n is the equivalence class of germs of functions, and it's a differential. And that's the abstract definition of one-jet bundle, but more concretely, it's nothing but the cotangent bundles times real number R. So you have a natural canonical coordinate QI, PI, and Z. So using that coordinate, we have a one form that is DG minus pullback of linearly one form to this one-jet bundle. So that can be just simply written as the DG minus sum of PI DQI. So the first law of thermodynamics can be regarded as the space that carries the contact structure. So let X1, Xn, and W be a set of n plus 1, forget about extensive, intensive. This is some statistical mechanics terminologies. So I would rather call them configuration variables. So I will write X1 through Xn, W as some configuration variables. And then Y1 and Yn and can be regarded as momentum variables. So thermodynamic phase space is nothing but just one-jet bundle of this way, the configuration variables. And then some thermodynamic process can be interpreted as some contact transformation. In other words, that preserves this contact structure on this one-jet bundle. The contact homomorphism is the diffeomorphism that preserves this contact structure, not just contact form, it's the contact structure. If the diffeomorphism preserves contact form itself, it's called strict contact homomorphism. But this object is not that interesting. Although physicists always uses strict contact homomorphism, but mathematically it's much less interesting than more general contact homomorphisms. So here is the example of some TPS that often appears in thermodynamics literature. So let's look at this configuration variable. Let's say X1, X2 is S and V. Here S is the thermodynamic entropy, and U is so-called internal energy, and V is a thermodynamic volume. And then this entropy and volume carries conjugate variables. That is temperature and negative pressure. And by the way, this thermodynamic and this entropy does not carry the conjugate variables because of this natural constraint. The probability average of probability density is 1. So there is no freedom about this expectation value of probability density because it's by definition it's going to be 1. So that is the reason why we do not have this conjugate variable for this entropy. And that is the source of odd dimensionality of this thermodynamic phase space. So contact form is written as here, but very often in thermodynamics, the physicists use the change of variables, keeping some thermodynamic some principles. Okay? So often we also use different choice of contact form. For example, ds minus 1 over t du minus p over t dv. And this leads to so-called entropy representations. So I gave you some examples of contact transformations. The first one is strict contact homomorphisms, in the sense that the contact form is fixed under that transformation. But the second one that changes the energy representation du equals TdS minus PdV into the entropy representation, that's ds equals 1 over T du plus P over T dV. That's not strict contact morphism, but the contact structure is still preserved. So I'm here repeating what I said. So the first postulate is that any change of thermodynamic representation should be a contact morphism on this TPS. Okay, so now let me talk about the second law of thermodynamics and how this second law is related to the geometric object Legendre submanifold in this contact manifold. So here is the one version of second law of thermodynamics. There are many different versions of second law of thermodynamics which are all equivalent, but I just took the most mathematical version of second law. The second law of thermodynamics at a microscopic level says that in an isolated system, any natural process in the system progresses in the direction of increasing entropy of the system. And so in an equilibrium state, the entropy is maximized. So in other words, in particular, the equilibrium state is some critical point of this entropy. This is very crucial element in the theory. So second law has been related to the difference between moving forwards and backwards in time. For example, entropy sort of is responsible for the presence of time, or to the principle that cause precedes effect, the so-called causality in this physics. Okay, so as I said, the equilibrium state is a critical point of this entropy. In fact, the information entropy. So the way how I'm going to describe the equilibrium state as the critical point of this information entropy. And this is some explanation about why the equilibrium state has anything to do with Legendre submanifold. Okay? So let epsilon be a submanifold, E be a submanifold representing a thermodynamic equilibrium. Then any vector field tangent to the submanifold should follow the thermodynamic first law, equilibrium thermodynamics. Therefore, eta should vanish on E first. Okay? So in other words, the tangent space of this submanifold should be contained in the contact distributions. Okay? That's what the first law actually implies. And then the note that in thermodynamics, classical thermodynamics, the equilibrium is usually represented as the thermodynamic potential with respect to given preferred variables. So in other words, at least locally, any thermodynamic equilibrium is represented as a Legendrian submanifold in the sense that it is a graph, one-jet graph of some potential function over the given preferred variable. So as I said, we often use different set of preferred variables in describing this equilibrium state. Okay, here is some example of Legendrian submanifolds. The most typical example is a one-jet graph. Okay, so you look at the configuration space and consider any smooth function or differentiable functions. defined on configuration space, and you look at the differential, that's one form, and then value of that function. You collect them all, and this is a prototype of Legendre submanifold. In other words, the contact form automatically vanishes on this submanifold, and its dimension is maximal for such a submanifold. And such a manifold is called Legendre submanifold. And by definition, the Legendre submanifold has dimension n in the ambient space of dimension 2n plus 1. Another more or less familiar but important example of contact manifold is projectivization of cotangent bundle with the zero section removed. Okay, so now let's talk about how we can use some reduction procedure to derive the macroscopic dynamics out of this microscopic dynamics of many-body particles systems. So as I said, I'm going to use two reductions. First reduction is happening in the symplectic setting, and the second reduction will happen in the contact setting. The basic principle is so-called Ness's principle that is very well known in Hamiltonian mechanics. So in the physics, the symmetry is represented as the group action on the space. For example, the translations symmetry corresponds to the momentum, and the rotational symmetries corresponds to the angular momentum. So the general Ness's principle states that each symmetry of a mechanical system in the phase space provides a conserved quantity which can be used to reduce the number of variables by 2. So when you're given mechanical system and you want to solve them, and you notice certain symmetry, then you can use this symmetry to reduce the number of variables, which would simplify the system so that it will help to explicitly solve the mechanical problem. And that's the way how the physicists in the end of 19th centuries, like Jacobi and Euler, Poisson, they did. They developed many different ways of utilizing these symmetries systematically in solving the mechanical problems by quadrature. And more abstractly, this Ness's principle has been formalized by the Marsden and Weinstein as a general reduction procedure called symplectic reduction. So here is the content. There is a very important geometric object so-called moment map. This moment map is defined as follows. You look at general symplectic manifold, and a Lie group acts on it, preserving the symplectic form. And then the moment map can be regarded as the collective way of considering all possible symmetries given by these group actions. Okay? So if the Lie group has more than one dimensions, and this collective symmetry will have many functions, conserved quantities, that satisfy certain relation, so-called Poisson bracket relation. And this is, moment map is some geometric gadget that unifies, that combines these collective symmetries. And formally, it is defined in this way. So the moment map is a map from symplectic manifold to the dual of Lie algebra. Okay? And this equation is just the defining equation of moment map. Psi M is a vector field generated by this Lie algebra element, Psi, for given group action. And then here is the symplectic reduction, sometimes also called Marsden-Weinstein reduction. This is the abstraction of Nesser's principles. So let M omega be a symplectic manifold, and Lie group G symplectically act on M. And then for each regular value of this moment map, the quotient manifold of the pre-image of this value mu by the isotropic group of mu. And this quotient carries naturally the reduced symplectic form. So you start with the original symplectic manifold where this Hamiltonian dynamics occurs. When you're given symmetries, you can reduce this, use these symmetries to do some reduction. So the way how the reduction by even numbers occurs, because if you take the preimage of some value that already reduced certain number by k, and then you take a quotient by g mu that gives you another reduction by same number k. And that's the way how this reduced space becomes always even-dimensional manifold. Not only even-dimensional manifold, it still carries canonical symplectic form. So the original Hamiltonian dynamics naturally reduced some reduced Hamiltonian dynamics on this quotient space. That's the content of this symplectic reduction. And in the statistical mechanics point of view, the thermodynamics is the macroscopic phenomenon arising from taking the average of the microscopic dynamics of a many-body particle system. Okay? So this process can be regarded as some reduction process, but now we are going to reduce the microscopic dynamics by infinite dimensional symmetries arising from some group of diffeomorphisms that preserves the observation or expectation values of some observables. So let me briefly talk about statistical and kinetic theory of phase space. Two important phase space occurring in statistical mechanics. One is the many-body particle phase space, which I denote by gamma. That's the cotangent bundle of R to the 3n. So this capital N is the number of particles. And then it carries a natural symplectic form, that's just direct symplectic form. And it has a natural measure, that's the Liouville measure. I will call this as the statistical phase space. And then, so one of the important operations in statistical mechanics is you should take some expectation value of some given observables. So what I mean by observables on this here is nothing but the general function on this SPS. Because SPS carries this measure, it is also called the random variables if you are familiar with the statistical mechanics. And in Boltzmann's theory, kinetic theories studies some dynamics on the space of these probability densities. So such an equation, so for example, Boltzmann equation is one of the examples of such a dynamics occurring on this infinite dimensional field space. So I will just repeat what observable is, and then you take the expectation values, but you can interpret this expectation value is just taking the observation of observables or you collect the average experimental data of the given observables. So this is some kind of averaging can be regarded as some kind of symmetry reduction by some diffeomorphisms that preserves this integral. So it's a very huge symmetry group because it just requires to preserve these expectation values. And then here is some interesting observables. This is this information entropy. Information entropy can be also regarded as some observables, but this is not a local observables. This is some observable which purely depends on the probability densities. Okay? So it's very unique observables. And what James observed is that this information entropy is the fundamental observables in statistical mechanics. So I'm just repeating the information entropy. So let me quickly go. Okay, and then this information entropy will play a fundamental role in deriving or giving the definition of thermodynamic equilibrium. So let gamma be a SPS, and each local observables, F, defines some expectation value functions by taking the expectation values. And then we can define the equilibrium state through, okay, so I said the equilibrium state is the critical point of these information entropy functions. But taking the, okay, maybe this one, I should go to, maybe, okay, so maybe I'll talk about this page first. So you look at this critical point equation of information entropy. This information entropy is defined on the infinite-dimensional field space. That's the space of probabilities. So first step of this solving the critical point equation will be the solve some constraint variation principle. So what I mean by this is you look at this collective observation. You're given finite set of observables. You regard this taking observations as some kind of moment map in this symplectic manifold, cotangent of probability space. You take this symplectic reduction. And here GF is nothing but the diffeomorphism that preserves the Liouville measure. It's an infinite-dimensional group. And this infinite-dimensional space is some kind of intermediate reduction from the kinetic theory phase space going to this thermodynamic phase space, which I call mesoscopic KTBS. And you collect this space over all possible observations. And here is the definition of mesoscopic KTPS. This is the kind of fibration. Okay, this is fibered over the observation data space. So in other, for each given observation or expectation values, you're given some infinite dimensional, some symplectic manifold. Not only that, this entropy function is reduced to some reduced entropy functions on this mesoscopic KTPS. Okay. So here is the reduced entropy function, which I will call this F-reduced entropy function. So this reduced entropy function is a function defined on this mesoscopic KTPS. Okay. So what I did here is to solve this critical point equation of entropy functions, I first removed this number of variables by applying some Lagrangian multiplier, because I look at the critical point equations for each given observation data. And here is the breakdown of that reduction procedure. The first step is finite dimensional reduction. So the fiber-wise critical point equations of the reduced phase function defined on MF defines so-called equation of motion. After you solve the first step, this one corresponds to solving some field equations. So this space will provide some kind of finite dimensional modular space, some equation of motions. That's what finite dimensional reduction, leading to this so-called TPS. So thermodynamic phase space is the space of some equation, solution space of equation of motion. And then this second step of solving the finite dimensional problem is happening on this thermodynamic phase space. So the non-equilibrium thermodynamic phase space is a Wonder space, and finding the equilibrium state is nothing but to solve these finite dimensional critical point equations. And through this process, you will get some Legendre submanifold or equilibrium state. What's happening is that this equilibrium state may not be a holonomic. In other words, it may not be the image of Wonder graph of function. Although it is always locally like that, but globally it may not be like that. So this is the actual source of phase transition. So I'll just quickly go over this so-called Van der Waals gas models. That is some kind of the most simple prototype of the thermodynamics where the phase transition actually occurs. So this is the gas equation for Van der Waals models. And here is the Gibbs free energy. And the Gibbs free energy is some thermodynamic potential associated to this pressure and temperature variables. Okay. And this is the actually equation, first the equation of Van der Waals model. That's the cubic equation for this volume. And we want to, here is the graph. This is so-called a PV diagram of Van der Waals models. So each this hyperbolic type of graph is the graph of that intersection of equilibrium with the PV plane. Okay? And this as the temperature changes, the graph moves like this. Okay? There's one particular temperature, which is denoted as here, that is like some inflection point, tangential inflection point. This is the critical temperature where the phase transition occurs. Okay, sorry. And here is the picture. So when temperature is less than that critical temperature, this PV diagram is like this. But this violates so-called stability. In other words, in thermodynamics, as in given temperature, in a closed system, as pressure becomes bigger, the temperature, the volume should decreases. But this graph violates it. So the Maxwell tried to correct this deficiency. What he did is, this picture is the so-called Maxwell's equal area law. Okay? And And then this is the picture of what Maxwell performed to find out the thermodynamic potential that is continuous. In this case, the Gibbs free energies. He wants to find continuous Gibbs free energies over this change of temperature. And this is the picture of the graph of this Gibbs free energy over the time or temperature changes. So as you see here, this function is not differentiable function at the particular temperature. But it is still continuous. Okay, so let me just, maybe this is worthwhile to quote. Here is a Maxwell's own quote. Since the temperature has been constant throughout, no heat can have been transformed into work. Now the heat transformed into work is represented by the excess of the area, FdE over dF. Here it is, FdE, here. FdE and BCD. So what he meant was that only when these areas are the same, you will get continuous function. Okay? Thank you.
네. 이제 질문이나 코멘트 있으면은 해주시면 감사하겠습니다.
May I ask a question?
Yeah.
Okay. So, gamma is a phase space, right? Gamma. And the P is the probability space on gamma, right?
Yeah, P gamma is a space of probability.
Then entropy defined on P gamma. Okay, why not? Why quaternion space?
You just lift. Any function on the configuration space can be lifted to a function on the cotangent bundle or one-jet bundle.
So originally entropy defined on. Okay.
Yeah.
네, 또 추가적인 질문이나 코멘트 있으실까요? 네, 그럼 제가 질문을 하나 드리려고 하는데요. 그 첫 번째 이제 도입 부분의 인포메이션 시어리 같은 것을 말씀하셨는데 그거와 중간에 말씀하신 서머다이맹스 컨택트 지오메트리랑 어떻게 관련이 있는지 그게 어디에서 들어가 있는지 조금 다시 한번 간략하게 설명해 주실 수 있을까요?
그러니까 the information entropy enters in the derivation of equilibrium, thermodynamic equilibrium. So thermodynamic equilibrium is the critical point of that information entropy.
네, 그렇군요. 네, 알겠습니다. 네, 그러면 좋은 강연을 해주신 오용근 교수님께 다시 한번 박수를 보내주시기 바랍니다. 네, 기조 강연을 마치도록 하겠습니다. 네.